Hello, everyone. My name is Chi Wang, or you can call me Aki. I'm honored to be here to share our recent research findings with you. The topic today is Break the Wall from Bottom, automated discovery of proto-level evasion vulnerabilities in web application firewalls. So in this talk, we will answer 3 questions. First, we will introduce the working principles of web application firewalls and their vulnerabilities. Second, we will talk about how we discover these new protocol-level WAF evasion cases automatically. Finally, you will learn how to bypass WAF at a protocol level like a pro. I will show you 3 useful tactics to bypass WAF at the protocol level. As we all know, modern web applications use parameters in HTTP requests to dynamically provide content to the cross-bounding user. For example, the web application shows the detail of product corresponding to the ID provided by the user. Since the input is not strictly validated, an attacker can construct a circle injection payload like this to steal the secret data from the web application. Today's web applications are facing huge cybersecurity risks just like this. Attackers can craft specific payload in HTTP requests to the vulnerable web applications so that they can execute arbitrary system commands or inject malicious cross-site script into web application. So aiming to protect web application from these threats, the web application firewall monitors and fleets out HTTP requests with malicious payloads like the circle injection payload. So compared to waiting for vendors to release their fixing patches and reconfigure the web application, deploying a web application firewalls to protect against the vulnerabilities of the web application is much more easier and much more flexible. So deploying a web application firewalls is one of the most popular protection for application nowadays. However, deploying a WAF does not mean you can rest easy. The battle between the attackers and WAF in cyberspace is never ending. As we all know, Log4j is one of the most damaging vulnerabilities in the history of Internet. And the research by the Cloudflare WAF team shows that attackers have been looking for ways to bypass the WAF. After the initial payloads get blocked, the attacker apply encoding ways and Log4j support features to try to bypass the WAF and launch their attack. So how does the WAF detect malicious requests? The working principles of WAF can be divided into 3 stages. First, it will paste HTTP messages to extract HTTP parameters. Then it will match the parameters with its roles. If any roles match the parameters, it will take action written in the roles. For example, in the figure, attacker trying to send with the circle injection payload in the JSON body, and WAF pastes the JSON body and then extract the parameters. Since the payload gets matched with the circle injection payload on upper, the WAF will reject the request, which means the request won't be forwarded to the server, and the attack will fail. So I know someone may say that this rule is so naive that I can easily bypass it, like using a greater than sign instead of equal sign, or converting the payload or to different cases. The attacker can mutate the original payload to a payload that's not in the roles of a WAF so that they won't be detected by the WAF. And you can see that the attacker can still launch a circle injection attack on the web applications, even if there's a WAF. So congratulations, you have discovered the payload-level evasion tactics. However, what if the rules become really mad? As the administrator can easily update their rules, they can restrict ID parameters and only allow numeric value. So in this case, can we still bypass the WAF and launch a circle injection attack? The good news is the answer is yes. Now let me show you the magic. The attacker changed the content type into x whatever plus JSON that will make the WAF silent, and the attack can still successfully launch a circle injection attack on the web applications, even if they didn't modify his payload at all. The reason behind these evasion cases is that the content type is not well known, and WAF don't recognize it as a JSON body. So the WAF will not paste it as JSON, and he can extract any parameters from the HTTP messages. However, as the code shows below, the web application developed with Wixer will accept any content type that starts with the applications and end with +JSON as a JSON body. So as we can see from the above example, the difference in how different parsers extract the parameters from the same HTTP request can cause the protection provided by the WAF to fail. Like if the WAF protects the web application A, B, and C, it cannot get the same result as these web applications do. It's actually hard for developers to fix these issues because the phases are built in the framework, and most of developers cannot change the logic. What was is that it's also a difficult problem for WAF because it knows nothing about this interface or what interface he is protecting. To sum up, we actually found two ways to bypass WAF. The first way is to craft a payload that is not in the roles of WAF. There are many WAFs that try to automatically generate a payload that can bypass WAF, like autospare and WAFManis. However, these approaches are limited to one specific vulnerability type, such as circle injection or cross-site script attack. And vendors can quickly block this payload by updating their rules. The second way is leverage the different pacing behaviors between the WAFs and the web application. And this does not only rely on mutating the payload, it can be utilized to load arbitrary attack vectors. Another advantage is that the approach still works well if the WAF have strict rules at the payload level, like only allowed numerical value. So in this talk, we mainly focus on the protocol level of WAF evasion. In fact, such tactics were proposed in Black Hat over 10 years ago, but we still find many new cases today. So after 10 years, the web application ecosystem has become more and more complex, and there's some parameters in HTTP messages. As you can see, that there are pass parameters, query parameters, head parameters, cookie parameters, and body parameters. And these are many new types of parameters in the body parameters. So the majority of protocol-level WAF evasion had been discovered manually in the previous work, which may result in some evasion cases being overlooked. So our question is how to systematically and efficiently mine for protocol-level evasion cases in WAFs. And we designed and implement WAFManis to help us to find the evasion cases automatically. The framework can be divided into two parts. The left part is the white box testing, and the right part is black box testing. We built an AFLI prototype to fast the HTTP request with the open source web apps in the black box testing. First, we collect the HTTP grammar and use them to generate initial samples. These samples are constructed with an AST, and they will line up in the crops waiting to be mutated, dumped to raw HTTP messages, and sent to web application validators. The web application executor will collect the code coverage and rearrange the queue in the crops to prioritize testing rules promising requests. In the black box testing stage, we will send the valid HTTP request that can be pasted by the web application's validators to the WAFs and correct their forwarder request to re-verify the request that can still be pasted by the web application validators. We also create an efficient sample centrifuge to minimize the request and feedback to the crops. All this verified sample will be stored in efficient samples. We will talk about these details in the following slide. So the talk is cheap. Let me first show how the framework works. First, we can configure the WAF address and the accept taint. In this demo, we choose SafeLine, one of the most popular open source WAF in the GitHub. The issue in this video has been fixed in the latest version. We have configured the safe line to most strict mode and enable all of the rules. You can see that WAF allow benign requests and block circle injection payload. Now we generate initial samples. Then we start to fast the evasion cases. The tool will first instrument the code of HTTP parsers. Now we accelerate the video, and you can see that we have found a lot of different evasion cases. You can see it as here. So let's try these cases. You can see that the cases still bypassed WAF we deployed. Still the data is OK, and the web app still correctly pastes the cases so that it can be used to launch circle injection to the web application. So it's great to see our framework works well and found new real-world evasion cases. To achieve this, we actually overcome a lot of barriers. Let me share with you how we address this challenge we meet. The first challenge is to generate and mutate the test input efficiently. Legacy further use raw HTTP messages as initial inputs and mutate the input with raw bytes. However, most of the mutated test input are incomplete or even missing payload in the body, leading to low-quality test input dominating the entire fuzzing process. To address this issue, we first designed the generator to help the framework generate initial inputs with HTTP grammar guidance. We first extract the ABNF grammar from RPC standards, and the generator will start to build AST from the start symbol. In this symbol, we start with the body symbol, and the generator will derive the symbol with the grammar into dash boundary symbols, body path symbols, and the closing boundary symbol nodes. This symbol will be further derived until they reach to the terminal node with raw strings. Then we get a fully expanded AST trees. And when sending to the server on the test, we will dump the AST into raw messages, like the one on the right. We use AST-based and payload-aware test input rather than raw messages so that we can freeze the payload node to keep the correctness and limit the search space based on the grammatical guidance. That's made the copycat happier. Another reason we stored our inputs as an AST rather than the raw messages is that we can mutate the test input in both grammar level and byte level. For grammar level, we can duplicate, delete, and remove a non-leaf node on the AST. For byte level, we can delete or add bytes in the leaf node and encode the leaf node. Specifically, we not delete or add bytes to the payload to ensure that sample can be further applied to any payload. The second challenge is to get effective feedback to guide the fuzzing process. The legacy gray box fuzzer like AFL collect the code coverage from the binary and source code. However, commercial WAFs, especially those software as a server cloud WAFs, are closed sourced without code or binary. So it's hard to get code coverage feedback from this. To address this issue, we choose to fuzzing the open source HTTP parsers rather than the WAF. We do this with two insights. The first insight is both WAF are implemented to parse HTTP requests with similar logic. So the code coverage of web applications can reflect the code coverage of WAF to some degree. The second is the more feature branch we covered, the more difference we will find. The third challenge is to detect successful evasion automatically. The legacy further determined memory bugs by programming inspection, panic, or harms. However, protocol-level WAF evasion are silent and won't trigger any inspection. And it must be benign at the WAF side while harmful at the web application side. What's more, the WAF may modify the original request messages, cause false positive or false negative. To address this issue, validators actually play an important role in WAFManis. They help the framework to recognize how WAF and web application process our test request. As the example code showed below, we developed web application file validators to echo the parameters it's actually using, like the request form and the request args. For web WAF validators, it will always return a special stage code and the exact HTTP request in its response. So even there are many ways that the WAF return a block page. We can quickly know the response are passed as soon as we see the special stage code in the response. And we can get the exact forwarding request to avoid the false positive caused by the normalization of the WAFs. To exclude false positive and false negative, we design a two-step validation workflow. In practice, we first send the test input to the web application validators. If it can bypass the WAF, we'll collect the modified request messages from the WAF validators and resend it to the web application validators for the second validation. So there won't be false positive. The last challenge we meet in practice is that there are too many duplicate evasion cases during the fast process. You can see that many successful evasion cases during the fuzzing process looks different, but with the same key point. So how to quickly find different tactics contribute to the evasion? We design and implement Centrifig to help us to minimize and re-verify the evasion cases. The main idea of the Centrifig is to iteratively remove the node in the AST and resend the sharp test input to the validator. After remove non-contributing nodes, we could find unique samples. For example, sample B is evasion cases. So after deleting the nodes, the Centrifig will minimize the sample A and the sample B. After we finish the key point of our design, it's time to look at what we found. In the evaluation, we select 20 popular open source web application frameworks and 40 mainstream WAF. For the setup of a tint payload, we use an unobfuscated attack payload that will be detected by the WAF without mutating the HTTP request at first. After the evaluation, we found two interesting facts. The first is that all test web frameworks accept non-regular requests. And the second is that most WAFs can be easily bypassed with specific HTTP requests. After manually analyzing these evasion cases, we summarize 3 protocol-level WAF evasion tactics named parameter type confusions, malformed parameters, and RFC spot gap. Let me show how these tactics help us to bypass the WAF. First of all, the parameter type should be identified correctly to help WAF extract the same parameters as the web application does. We found that we can make a fake con type header to mislead the WAF to choose the wrong type to face the body parameters. In this example, the ModSecurity thinks the body is XML, while the Flex application will use the last content type headers to indicate the body type, which is URI encoded. After reading the related code snap, we find that because the dependency library uses a dictionary to store the head value, the Flask web application will always choose the last head value. The next case is the listing the WAF to synced parameter is a binary file rather than a query parameter. In this case, the attacker added 2 CR characters and a fake content transfer encoding header with file name parameters. We found that Alibaba WAF will consider a single CR as a line termination, while the PHP won't. That made WAF pass a valid file name parameters and indicate that this part content is a file. Since the file content is rarely used to compose circle commands, the WAF won't apply circle injection rules to these file parameters. However, the attacker can use these tactics to launch circle injection attack on the PHP-based web application. For tactic 2, attacker can construct malformed data that the WAF won't paste while the web application can. The difference against the tactic 1 is that while the WAF chooses the correct parser, it can not extract the correct parameters while the web application can. In this example, we found the interesting fact is that Cloudflare WAF cannot handle boundary parameters with quarter. When the attacker crafts a boundary with quarter, most of web application will remove the quarter and paste the HTTP body. However, the Cloudflare WAF won't get the correct parameters in the body, so that the attacker can leverage this tactic to launch circle injection to the web application. In this case, we found an interesting fact that PHP-based web applications are very tolerant of malformed HTTP messages. After the attacker had deleted the closing boundary and the form data token in the content disposition, the PHP-based web applications can still extract the correct parameters like this, while the Fortinet WAF don't, because the body is too malformed. So with the help of the scientific model, we also found the smallest body that PHP can tolerate as a valid multiple-part request. You can see that the left one is the normal multi-part data request, and the right one is the minimized one. The PHP-based web application can still paste the correct ID parameters, even though the body parameters and the closing boundary token are missing. And there is no line termination between the headers and the body. So the attackers can leverage this tactic to transmit any attack factors and evade the detection of WAF. For tactic 3, we found that there are many deprecated or extended features in related RFC standard. Attacker can use features support in web applications, but not support in WAF to evade the detection of WAF. The difference between the tactic 2 is that the attacker actually crafts a formal request that should not trigger the WAF's pacing inspections. In this case, we found that Go-based web app will automatically decode with the content transfer encoding header. So this encoding data will be decoded to this circle injection payload. However, in RFC 7578, this feature is deprecated and almost no WAF supports this feature, so that the attacker can leverage this header to encode their payload and evade the detection of WAFs. The root cause is that the MIME library of Go SDK still supports the content transfer encoding headers. So when the content transfer encoding values the code printable, it will automatically decode it. In the case 6, we found that the Django app supports cherry set parameters even when the content type is URL encoded. And in most WAF parameters on these MIME types, the cherry set parameters will be ignored since no document or standards had recommended. So actually, the attacker can use these tactics to bypass almost any WAF and attack the Django app. since in the version of the WAF, it cannot decode this data. So after we found these cases, we checked the code and found the Django will use the cherry set parameters in the count type to decode the body parameters. It's quite interesting. So we totally found 311 evasion samples across 40 by 20 WAFs and web application combinations. We have seen that some WAF are very strict, like Nessus and ModSecurity, and some WAF, they didn't paste the body. But we still find approaches to bypass this WAF. Like for those WAFs that do not paste the body, we can use the encoding tactics to bypass their detection. And like ModSecurity and Nessus, we can use the content type smuggling tactics to mislead them to use the wrong phases. After we discovered these efficient cases, we soon report them to the related vendors. Specifically, when the root cause is that the web application didn't follow the standard, we choose to report to the web application firewalls frameworks. Until now, 11 vendors have received the report, and 9 vendors have confirmed with 8 vendors fixed. So to sum up, our work underscored the unfortunate fact that the pacing process has become the Achilles heel in WAF defense. So the pacing parameters giving WAFs visibilities, but also create a vulnerability. We design and implement a new protocol-level efficient parsing framework called WAFManis, which can mine protocol-level WAF efficient vulnerabilities with code coverage guidance. We summarized 3 tactics in payload-level WAF efficiency and found 311 efficient cases on 40 by 20 web applications and WAF combinations. So this is my share today. Thank you all for your attention.